For a charge Q at the origin, we know the form of the electric field intensity. I'm going to use R' to designate the position vector of location P. The potential difference between location R' and infinity is the amount of work to move 1 coulomb of charge from infinity to R'. We can find that work by taking negative the integral from infinity to R', the electric field intensity dotted with our differential length. When you see this equation, your mental model should be 1 coulomb times the electric field intensity is a force dotted with dl, a differential length, is a differential work. Summing those differential works from infinity to R' is your potential difference between these 2 points. We've previously substituted our electric field intensity for point charge and done this integration. The result is Q over 4 pi epsilon sub 0 times the distance R'. Now let's change the location of our origin to this point here. The position vector of charge Q is R sub Q, and the position vector of location P is R. Now we want to find the potential difference between location R and infinity. Where we place our coordinate system is arbitrary and does not affect what is physically happening. The amount of work to move 1 coulomb of charge from infinity to point P does not change when you move the origin of your coordinate system. This equation, Q over 4 pi epsilon sub 0 R', is still the amount of work to move 1 coulomb of charge from infinity to point P. So our potential difference between point P and infinity is still Q over 4 pi epsilon sub 0 R'. We can find R' reference to our new origin. R' is equal to R minus R sub Q. So the distance R' is just the magnitude of R minus R sub Q. Now let's suppose we have n point charges and we want to find the potential difference between point P and infinity. We know superposition holds for finding the electric field intensity. We can find the electric field intensity due to each individual point charge and then do a vector sum of them. The potential difference between location R and infinity is minus the integral from infinity to R of E dot dl. We can break this integration into n integrations, one for each individual point charge. Each one of these integrations is the amount of work to move 1 coulomb of charge from infinity to location R if only that one charge were present. To obtain the amount of work to move that 1 coulomb from infinity to R if all the charges were present, it's just a summation of all these terms, which is equal to the sum from k equals 1 to n of q sub k over 4 pi epsilon sub 0 times the magnitude of r minus r sub k. This magnitude of r minus r sub k is just the distance between that particular charge and the location of the potential. Let's now look at the situation where we have some charge distribution, in this case a volume charge distribution. We want to find the work to move 1 coulomb of charge from infinity to location R. We know how to find that potential for a point charge, and we can treat this charge distribution as point charges. Each differential volume has a point charge associated with it of rho sub v dv. We'll use the variable r' to designate the position of our differential charge packet dq. So the amount of work to move 1 coulomb of charge from infinity to location r with this dq present is rho sub v dv over 4 pi epsilon sub 0 times the magnitude of r minus r prime. The magnitude of r minus r prime is just the distance between our differential charge and the location we're trying to find our potential. To get the final result, we just integrate over our charge distribution, summing up each of those individual contributions to the potential at location r.